Hello dear students. So we are starting a new topic, that is lateral earth pressure, for this course C5202. Now what is lateral earth pressure? Suppose I have a soil element Let me draw a soil element. Suppose this is my soil element, and it is the soil element is within the soil mass. Therefore, obviously, the vertical pressure due to overburden or due to some surface load is acting on it. Let me call it, say, sigma z. We are thinking about the normal stress only on this plane. Now, due to this sigma z, since the soil is confined, therefore it will also develop some normal stress on the vertical planes, right? It will also develop some normal stress on the vertical faces in both the directions, and these are, we are denoting them as lateral pressure, which is sigma x in this direction, and say in this direction it is, say, sigma y. Alright, and if my soil is isotropic and homogeneous, then at some depth z, when sigma z is the vertical pressure, vertical stress, then sigma x and sigma y will be usually equal if the soil is within a soil mass, if the element is within the soil mass which is homogeneous and isotropic, right? Now, in many design situations, knowing this sigma x or sigma y becomes very important. For example, if I want to design a retaining wall or a sheet pile wall, or say basement wall of a building, then since the wall will resist the load from soil, the wall will be subjected to some lateral pressure, earth pressure, and that pressure, determination of that lateral pressure is important job of a geotechnical engineer. Now, I may have three types of earth pressures depending on the condition of deformation within the soil mass. One is earth pressure at rest. Earth pressure at rest means it is the lateral stress that is developed when the soil is not allowed to deform laterally, because the soil element is within a infinite or semi-infinite soil mass. Therefore, when the soil element is in its natural condition, suppose this is my ground level and I am considering the element within the soil mass, because the soil is extended to infinity in both x and y directions. Therefore, this element cannot deform laterally because it is totally confined, and whatever stress that acts under such a condition, whatever normal stress acts on the lateral faces of the element is called earth pressure at rest. Okay. Similarly, if I allow, suppose the second condition, that is active earth pressure, occurs when I have a, say, retaining wall, something like this. Let me draw a small retaining wall. Say this is my retaining wall, and it is retaining some backfill soil. It may be a man-made backfill or it may be a natural cut. Suppose there is a highway here. Okay, there is a highway here or embankment. To retain the soil of the cut, I need to have some retaining wall, and this retaining wall, if this retaining wall moves away from the backfill due to the lateral pressure, then what will happen? Some lateral stress will act on this retaining wall or at the soil element very near to the retaining wall. If I assume a soil element very close to the retaining wall, let me draw another rectangle. Suppose this is a soil element very close to the retaining wall. So when I am allowing this lateral deformation of the wall away from the backfill, basically what I am doing, I am reducing the confinement of the soil element, and therefore after sufficient distance, what will happen, after sufficient distance of movement of the retaining wall, what will happen, some portion of the soil will try to move along with the retaining wall. All right, along with the retaining wall. Suppose this portion of my backfill behaves as a chunk and tries to move away from the backfill. So the sliding mass of the soil will be moving downward. Sliding mass of the backfill will be moving downward, and the shearing resistance of the soil will act upward, just to oppose it. Okay, and this condition, when the soil mass near the wall is at the verge of failure, due to the movement of the retaining wall away from the backfill, whatever lateral pressure acts on the soil or the wall is called active earth pressure. All right, that is what is active earth pressure. So this is my active condition. Okay, so here what is happening? Here the soil is actively pushing the wall away from the backfill. That's why we call it active. In the other case, what happens? Just opposite of this active case can happen. Suppose I have a retaining wall, the same retaining wall, and the backfill is there in this side. In this direction I have the backfill. Now suppose due to some reason the wall is pushing the backfill. There can be different condition, real condition, where this situation arises. In that case, what will happen? My vertical stress is remaining same within the soil element. My vertical stress, again let me consider a soil element near the wall. My vertical stress is, say, sigma z. Now what I am doing, I am gradually increasing the lateral stress, sigma x, so that ultimately after sufficient movement of the wall towards the backfill, this is moving towards the backfill, after sufficient amount of movement, what will happen? A chunk of the soil near to the wall will move, will fail, and then will slide upward. All right, will slide upward in this case. So this is my movement of the failed soil mass, and in this case my soil resistance, shear resistance, will act downward. And this condition is called passive condition. Now in all these three conditions I will have different amount of lateral stress. The maximum lateral stress will be under the passive condition, and the minimum lateral stress will be at the active condition, and in between there will be the at rest soil pressure. Now while finding lateral earth pressure, we try to relate the lateral earth pressure to the vertical stress that is acting within the soil mass. That means let me call the lateral pressure as sigma h, because it is acting in the horizontal direction predominantly. Now I want to express this sigma h as some function of sigma v. Why I do that? Because I know that it is relatively easier to calculate the sigma v or sigma z, because if I know the depth of the backfill, if I know the gamma, then at any depth I can easily calculate what is the sigma z. Say if I consider this soil at this soil element at a depth of z, say this is my z measured downward from the ground level, then if the soil is gamma, then I know that my sigma z is how much? It is gamma times z. Okay, if there is water table, then I will have gamma saturated times z will be the total stress, and the effective stress will be gamma submerged times the z, and so on. So since it is relatively easier to determine the overburden pressure or the vertical stress at any point. Therefore, if I can express this horizontal stress or the lateral earth pressure in terms of this vertical stress, then this becomes, the calculation of lateral earth pressure becomes easier. Okay, and that's why we define a ratio of horizontal stress to vertical stress. I can also call it as, say, sigma x by sigma z. This ratio is denoted by a letter k, and this is called coefficient of earth pressure or earth pressure coefficient. Earth pressure coefficient. Now our job then to find out the lateral earth pressure, our job basically is to determine the coefficient of earth pressure. Now since the amount of earth pressure will be different in these three conditions, namely at rest condition, active condition and passive condition, therefore this coefficient of earth pressure will also be different in these three conditions. So I will have earth pressure coefficient at rest, I will have active earth pressure coefficient, and I will have passive earth pressure coefficient, and they are respectively denoted by K naught for earth pressure coefficient at rest, then Ka for earth pressure coefficient at under the active condition, and Kp for the coefficient of earth pressure under passive condition. So our, in the determination of lateral earth pressure, our first job basically boils down to determine what is K naught, what is Ka, and what is Kp. Okay. Okay, now let us find out the earth pressure of at rest coefficient, that is the coefficient of earth pressure at rest or earth pressure coefficient at rest, K naught, on the basis of elastic theory, because that is the easiest one. And elastic theory. So here we are assuming that the soil is homogeneous isotropic elastic solid, and therefore based on your three-dimensional elasticity, suppose I have this soil element I am considering at any depth z, it has a vertical stress sigma z and lateral stresses sigma x and sigma y, and because the soil is isotropic and since there is no deformation, no lateral deformation, therefore my sigma x and sigma y are equal. Okay, so my soil is isotropic, and therefore I have sigma x is equal to sigma y. Now at rest condition means there is no lateral deformation, that means there is no lateral strain. So let me write down the expression for lateral strain in x direction, epsilon x, normal strain in x direction. This will be given by what? Sorry, one over E times the stresses in x direction. Okay, and the stress in x direction is sigma x, that is the direct normal stress, and due to Poisson's effect I will have nu times sigma z plus sigma y. So this is my total stress. This is my total stress acting in x direction considering the Poisson's effect, that is the lateral deformation, and that stress divided by E gives me the strain, and I know that this is equal to 0. Okay. Now I also know that sigma y is same as sigma x, therefore I will write this equation as say 1 over E times sigma x minus nu, which is the Poisson's ratio, into sigma z plus sigma x again, and this is 0. Now since E cannot be 0, therefore these terms within the square bracket must be 0 for no lateral strain, and therefore I can write that sigma x must be equal to nu times sigma z plus sigma x, and therefore I can solve it for sigma x. So sigma x times 1 minus nu will be equal to nu times sigma z, right? And therefore I can find out the ratio of sigma x to sigma z, which is my k naught, and therefore from here I get sigma x by sigma z will be my nu by 1 minus nu. Okay, and by definition this is what is the earth pressure coefficient at rest, is not it? So I can say that k naught is equal to nu by 1 minus nu. I'm sorry, my handwritings are becoming very bad because it's quite difficult to write here, not so easy. So we get k naught equal to nu by 1 minus nu based on elastic theory. Now the problem is, we know that soil is not really an elastic material, and therefore it is not easy to determine the Poisson's ratio, because most of the time because the soil is not elastic, it will behave as a non-linear material, elastoplastic material, and so determination of Poisson's ratio will not be very accurate. And therefore what we do, we depend on the empirical relations based on the field tests, all right. Now as elastic theory is not strictly applicable in soil, therefore the value of k naught obtained on the basis of nu or Poisson's ratio is not much reliable. So we use the empirical test results and the empirical relations given based on these test results for finding k naught. and they are believed to be more reliable. And there are various empirical relations given by different authors. The most famous one is by Jackie. So next we are discussing empirical relations. Empirical relations. For K0 value. So the Jackie's equation gives K0 is equal to 1 minus sine phi dash, and this is originally given for sandy soil, but then it is also used for normally consolidated clays. So for sands and NC clays, K0 is given by 1 minus nu. Then there are other relations like this is by Jackie. Let me write down. It's pretty old relation, 1941. Sorry, 1944, just after Terzaghi published his first book on soil mechanics. The name of the book was Erdbeomechanik in German, and that actually is supposed to be the starting point of soil mechanics or geotechnical engineering. Then there is another relation by Brooker and Ireland. Brooker and Ireland. And this was from 1965. They gave cannot equal to .95 minus sine phi. Minus sine phi plus 0.15. Similar to this value actually, 0.95 plus 0.15 gives me 1.1. So instead of 1 they have given 1.1. Okay. Then for Encycles, Alpan gave another relation. Alpan in 1967. K0 equal to 0.19 plus 0.233 log of plasticity index. Okay, and this is true for Encycles. whereas for Ocycles it says K0 for NC times root over OCR, where OCR is over consolidation ratio. This is for Ocycles. So a similar relation, a more recent relation given by Maine and Kulhavi is I'm giving all this for the sake of completion, but most commonly used one is the Zecchi's equation, which is easier to remember also, so you may just remember that equation for the time being. Maine and Kulhavi. In 1982, they give the equation as K0 equal to 1 minus sine phi sine phi dust into OCR to the power sine phi. Okay, so these are some empirical relations given by different authors. So next we'll be discussing the earth pressure for active condition. Okay, so our next topic is active earth pressure coefficient we can also discuss this at the same time, the passive earth pressure also. Because they are very much they can be explained by the same basic concepts from more circulate failure. Okay, for that purpose let me draw one coordinate system for you. Then now both active and passive condition occurs when there is lateral deformation of the wall or the backfill. Yes, so in active earth pressure the wall moves away from the backfill, that means backfill actively pushes it away, and in passive earth pressure the wall pushes the backfill. That we have already discussed in the earlier portion of the class. So this is our active condition, this is our passive condition. This we have already seen. Now there is something called Rankine's active or passive earth pressure theory. So we'll be discussing Rankine's theory now. Rankine's theory. This was one of the very old theories of soil mechanics. Actually, Coulomb's theory and Rankine's theory both were used for retaining wall design before there was geotechnical engineering. Okay, basically they used plastic theory of plasticity, and this was the design of retaining wall was one of the very earlier practically needed civil engineering job. Those days the engineers were only civil and military engineers. In fact, Coulomb was a military engineer who was in charge of constructing some forts in the Caribbean islands. He was a French person. He was a military engineer for the French king at the time. I think it was 1772 or something like that. And for a rational design of the fort walls, which were retaining walls, he tried to develop some theory which today we call as Coulomb's earth pressure theory. Similarly, Rankine also independently developed another theory. Now let us see what are the Rankine's theory assumptions. As usual, he used soil to be homogeneous and isotropic. Soil is homogeneous and isotropic. Then he assumed that plastic equilibrium occurs. So soil is a rigid plastic material. Then he assumed that there is no friction between soil and wall. Soil wall interface is frictionless. Okay, we are assuming frictionless so that the soil element very near to the wall, there is only normal stress on the vertical surface. That means on the soil element parallel to the wall, say I have a wall here, okay, and very near to it I have a soil element. Because there is no friction in between, therefore this plane doesn't carry any shear stress, and so any stress will be only normal stress. Okay, any stress will be only normal stress. That means there is no shear stress, only normal stress, so it will be a principal stress. That's why he assumed that soil wall interface is frictionless. Okay, similarly he also assumed that backfill surface is horizontal, so that it is again free from any shear stress. Backfill surface is horizontal. So these are some important assumptions of Rankine's theory. Now, using this theory, let us now analyze the amount of active and passive earth pressure for a given soil element on which the vertical stress acting is, say, sigma z or sigma v. Okay. Now if I draw that sigma v, if I draw a Morse circle for that condition, initially the soil will be at rest condition, no lateral strain. Therefore what will happen, if the soil, the vertical stress on the element is, say, sigma v, say this is my sigma v in some scale, this is my value of sigma v, then my sigma h will be how much? K naught times, it will be K naught times sigma v, right? Because it is at rest condition. So at rest I have sigma h is equal to K naught times sigma v or sigma z. Okay. Now if I draw the Morse circle for these conditions, then I will get a circle. So let me draw a circle. Let me take dotted line now, or dash dotted line. So say this is my circle, Morse circle, when the soil is at rest condition. Okay, so this is my sigma v, this is my K naught times sigma v or sigma h. Now suppose I move away the wall from the backfill, that means I allow active condition to take place. I allow active condition to take place, and in that case what will happen? In that case, that means since my confining is becoming lesser and lesser due to wall movement, I will be actually reducing the horizontal stress, right? Horizontal stress, and therefore my circle will grow larger and larger, it will start from here, and then then I'll have a more and more decreased value of horizontal stress, and finally I will have a condition at which this circle will touch my Mohr Coulomb failure envelope. Okay, suppose I have a Mohr Coulomb failure envelope here, and now the circle is such that it has failed, the soil has failed, soil element near the wall has failed or is at the verge of the failure. Okay, so that's how what I am doing, I am keeping my sigma h constant, sigma z constant or sigma v constant, and I am reducing the sigma h up to this value such that it touches the Mohr Coulomb failure envelope. Okay, I am assuming a cohesionless soil now. Well, Rankind's theory originally was given for a cohesionless soil, and therefore that is another assumption, that soil is cohesionless. I forgot to mention this. Soil is cohesionless. Soil is cohesionless. So this is another assumption. Now when it fails, you know that suppose this is my center of my circle, okay, and therefore I can draw a perpendicular here. I can draw a perpendicular from this point to the center. Say this is my center, this is perpendicular, and from this you know that this will be my pole of the Mohr circle. Let me slightly zoom in so that you can see it better. Now if I draw a line from here, this is my pole of the circle. Why it is pole? Because pole, you remember, is that point through which if I draw a line, if I draw a horizontal line, it will meet at a point on the Mohr circle which represents the stress condition on a horizontal plane. Now this was my sigma v. Sigma v will be acting on a horizontal plane. So I am drawing a horizontal line from here, and so that's why this must be the pole, right? This must be the pole, and therefore if I draw the line from here to this failure point, this will give me my angle of failure plane. Angle of failure plane. Sorry. This is my angle of failure plane, say theta 1, and you remember from the geometry of the Mohr circle that this theta 1 is how much? Theta 1 is 45 plus 5 by 2, right? Earlier probably we used the notation alpha for this angle in C4103. This is my angle phi. This is my angle phi, and therefore how much is this? This is 90 plus phi, and because this and this are equal, the radii of the same circle, so this angle and this angle is same. So this plus this must be 90 plus phi, therefore this angle is 45 plus 5 by 2. You remember all this, I suppose. So this is how the active condition takes place. That means in the active condition, when this occurs, what has happened? My soil is at the verge of failure, and therefore my failure planes will be developed at an angle of 45 plus 5 by 2 with the horizontal direction, okay, and that is my active condition. So let me draw it once again. Say this is my retaining wall. I am assuming a vertical retaining wall, remember, so that this is a principal stress, principal plane. This plane is a principal plane, so this is a principal stress. Now say this is my backfill surface, okay, and this is my angle of failure plane in the failure wedge will be the same theta 1, okay, and there will be many parallel lines like this. because the whole mass is failed. Okay, and just like this I can have also another set of failure plane in the opposite direction. Let me draw it. Say this is my More Coulomb failure envelope. So I have a similar point here. I have a similar point here at 90 degree, and this is another set of failure plane. Sorry, having the same angle θ1, and this is my θ1 again. All right, so I have another set of planes making 45 plus 5/2 with the horizontal. So these are my failure planes that will develop in the active condition. Clear? So this is how Rankine analyzed the active earth pressure. Now you see, how can I find out the active earth pressure now? The value of Ka by knowing the relationship between the principal stresses at failure. You see, this is my sigma 1, or the major principal stress, which is equal to sigma V in active case. Okay, and this is my sigma 3. This is my sigma 3, which is equal to sigma H in active case. And you already know that the relationship for a C5 soil, the relationship between the principal stresses at failure was what? Do you remember? It was sigma 3 equal to one minus sine phi by 1 plus sine phi let me raise this page a little bit into sigma 1 minus twice C into root over of this quantity. I'm sorry, 1 minus sine phi by 1 plus sine phi. Okay, this relation I think you remember already. This relation we have studied in the first course of our soil mechanics, or geotech 1. So now when I put for a cohesionless soil, when I put C equal to 0, then sigma 3 becomes this much into sigma 1, or as I have already shown you that sigma 3 is nothing but sigma H, sigma 1 is nothing but sigma V. So relationship between sigma H and sigma V is given by, so sigma H, sorry, sigma H is this quantity 1 minus sine phi by 1 plus sine phi into sigma v. That means this is the value of my coefficient of active earth pressure, or I write Ka times sigma v. Therefore my active earth pressure coefficient Ka is simply 1 minus sine phi 1 minus sine phi by 1 plus sine phi. Clear? So this is what is the formula for coefficient of active earth pressure for a cohesionless soil. Okay. Next, let us go to the passive condition. Now in passive condition, what will happen? In passive condition, once again I will have the same sigma v. Okay, if I am considering the same soil element near the wall, I have same sigma v, but this time wall will move towards the backfill, right? Wall will move towards the backfill. So wall will move towards the backfill, and therefore what will happen? My sigma 1 or the horizontal stress will gradually increase until the failure occurs. So what will happen to the Morse circlet failure? I will again start a circle with the same sigma v, and now my sigma h will go on increasing, so my circle will move in the opposite direction, and finally at failure it will just meet the failure envelope. Okay, so gradually now I am increasing sigma h, and this time this value will be sigma 1, isn't it? So these values, these let me write it. I'm sorry. For active case, this is my sigma 1, okay, or let me call it sigma z for the time being. Let me draw a line, and this is my sigma z here. Okay, sigma z here, and this is my sigma h in case of active condition. Now in passive condition we see that this sigma z is my minor principal stress now, and this sigma h is my major principal stress. So in active condition what will happen? Sigma 1 will be my sigma h. Okay, and now for this circle this will be my pole. Why it is so? Because this is my sigma z that is acting on a horizontal plane. So if I draw a horizontal line through this point, it will meet here. That means this is my pole. So my origin of planes is this point, therefore my angle of failure plane will be what? My angle of failure plane will be from this point of tangency to this pole. I'm very sorry. Say this is the line showing failure, angle of failure plane. And now if I draw a perpendicular at this point, this is my center of the Mohr circle, okay, and therefore this angle is my 90 plus phi, okay, this is my theta, say 90 plus phi, and therefore what is this angle from a horizontal plane? This angle must be this is what? This is my 90 minus phi, external angle, 90 minus phi. So this plus this, which are equal, will be equal to 90 minus phi. So therefore this will be half of 90 minus phi, which is say theta 2 will be half of 90 minus phi, so it will be 45 minus phi by 2. So in the passive condition, my failure planes will be inclined with horizontal at an angle of 45 minus phi by 2. So if I draw those failure lines, this is my active condition. Let me write it. Active. This angle is theta 1, and in a similar case let me draw another retaining wall. This is my backfill surface. Now I will have a larger wedge because this line has to make an angle. This line should be parallel to almost this line, okay. So all my lines, failure planes, will be parallel. Alright, this is one set and another set will be parallel to this line, so I will have something like this, maybe. Alright, and so when the whole mass fails, this will be my theta 2, okay. I'm sorry, this angle, these angles are my theta 2. Alright, so this is my passive condition. So this is how on a vertical wall Rankine's active and passive state occurs, thereby brings the soil to failure, and the active earth pressure we have already found from the relationship between sigma 3 and sigma 1. Now in passive case, what will happen? My sigma 1 I should express in terms of sigma 3, because this is my passive Morse circle, right? Let me write it down. This is my passive failure circle, and this is my active failure circle. So you can see that soil can fail in loading, that means increasing sigma 1, or even unloading, that means decreasing sigma 1. Okay, and this shows that earth pressure at rest is in between the active pressure and the passive pressure. So earth pressure at rest is somewhere in between the active and passive pressure. So minimum pressure at failure that is necessary is the active earth pressure. The maximum lateral pressure that causes the failure is passive earth pressure, and when the soil doesn't fail, it is without any lateral strain, then the lateral stress acting on it is my earth pressure at rest. Okay, so let me write this also, that this is my at rest condition. At rest condition. So I think this makes it clear how the principal stresses are related to active and passive earth pressure. Now in passive case, my sigma 1 I need to express in terms of sigma 3 from the Morse circle, geometry of Morse circle, and this also we have already seen. In fact, the same equation I can use, just I can solve this for sigma 1 in terms of sigma 3, then we will get this. Also we had studied in our Geotech 1. We will get sigma 1 will be equal to sigma 3 times 1 plus sine phi by 1 minus sine phi plus twice c times root over of this same factor, 1 plus sine phi by 1 minus sine phi. Okay, so for a cohesionless soil, my sigma h in this passive case will be sigma z into coefficient of passive earth pressure Kp. Therefore Kp will be 1 plus sine phi by 1 minus sine phi, or just inverse of Ka. This is nothing but 1 upon Ka. This also we have seen. Okay, so this is the formula for passive earth pressure coefficient. So these two relations we have derived today based on Rankine's theory of active and passive earth pressure. We have also seen how the failure planes are oriented in active and passive cases. All right, so with this we stop this part of lecture.